Uh, in next couple of slides, we'll be looking at a summary of all the important topics that we as social scientists should know, right, for performing any sort of social network analysis, social computing, or data mining, right? So we started with sort of the history of internet, where the internet was before, how it has evolved, and in which direction we are moving. We started from a read-only billboard, where any website was more of a notice board, where a lot of information is there. You can only go there and read. That's it. You cannot interact, you cannot talk, you cannot post anything. Then we moved on to the Web 2.0, which is called the social web, where each person has the power to post something, to like or dislike something, to connect with other people. This kind of internet came up, right? Say last 20 years. Right now we are moving towards Web 3.0, which is more of a semantic web. Semantic as in the way in which data is stored on the internet. It has a internal meaning or tagging, so that any program, any software you write to mine data or extract data can understand the underlying connections also. So this is mainly for a machine processable meaning. Basically, computer should understand, if I'm fetching data from different portals, different platforms, how the data is connected, what is the internal structure of the data, rather than just doing a string search. So there was a knowledge gap in the social web, where if I search for Paris, the computer will only search for PARIS. But as humans, either we are searching for the city or Paris Hilton, the actress, or something else. So this kind of semantic meaning, semantics as in the understandable meaning or the context of the problem, was missing. So the computer got confused whether computer will see strings, but humans see the meaning, either city or a celebrity, right? So from there, we moved on to how do we make sense of the data that we collected online through forms, through some sort of qualitative analysis, or we interviewed a lot of people and collected data. How can I create a mathematical model out of it? So we looked at adjacency metrics, where you put so any graph, any social structure will have nodes and edges. Nodes are people, entities, organizations. Edges are the relationships, or how are they connected. Like you message someone once or twice, or you hear back from them, you create an edge. So, but graph is a one way of representation. Other way is to have a adjacency matrix, which shows you that if there is a number at any cell, that means the row and column are connected by some means, and you can add more numbers. Say the higher the number, the stronger the relationship is, right? Suppose this is a table about four friends, how much this exchange memes with each other, right? Wherever is zero, there are no memes exchanged. Wherever there is one, there are exchanges. But we do not know what is the level of exchange, what is the strength of the relationship. So you can increase the number, say 1 means 1 message, 100 means 100 messages or memes exchanged, right? Then there is this sort of, this is a symmetric graph where you are exchanging information. All the nodes are equal and they are exchanging information, but is it directional, right? Sorry, undirected, because you can send and receive the messages. But there could be an actor by event mode matrix, which is more of used in terms of organizations, right? To understand, say, I want to understand I think we saw this example where we want to understand how a city works. There is a municipality division, there are political groups, there are organizations, how do they connect with each other? So it's more of a directed one. So basically all these A1 report to E1, A2 reports to E1 and E2 and E3. So this kind of a directional. So graph could be asymmetric or non-directional, or it could be directed graph, right? And we also looked at, like, any social network is a small world which have high clustering and low average path. So we looked at the example where I want to send a letter to Shah Rukh Khan. We thought that it will take a lot of connections and a lot of steps to reach my message, to reach Shah Rukh Khan. It will take a lot of steps, but in reality, it is not true. Real world, we have a lot of connections, and the average, the shortest path, the average of shortest path to any person is very small. So we looked at around 6 degrees of separation. That mailman example we did, where a person has to send a letter to a specific person which he does not know. So he asked all of his connection to send this letter to one of the people they know already, until the letter reaches the person which was intended to. right? And it took around 6, 7. So it is not exactly 6, but a smaller number. So maybe you can reach to an unknown person in 5 steps or 10 steps or 15. The average is low. As compared to, suppose I were to send a message to Messi, it will take, say, 100 connections. It's not like that. Maybe 10, 20 connections, I'm able to reach to Messi. This is what Raj Shamani is using for getting the podcast. He knows someone who can know the person he wants to invite. So that's how it works. Then we looked at a lot of measures of centrality, right? So we first of all we looked at, suppose this, we took the example of this class. There are multiple students. All of these are students. They are connected, maybe directed or indirected. But we looked at degree centrality, which is basically the most number of connections, the most popular person who talks to a lot of people, and a lot of people talk to him, right? In our case, could be the CR of the class. Next, we looked at the betweenness centrality. Basically, it is like the bridge or the gatekeeper that for any network, the information flow in a network, this particular person comes in the shortest path of most of the people, right? Suppose in your case, again, it will be the CR, because any communication you want to do with the teacher or the admin group, you have to talk to the CR. Right, given his position, the CR position is the highest between centrality and also the degree centrality, given his role. Right. Then there is this closeness centrality, which has the shortest path to all the people. Okay. Basically, he can reach every node in the graph in minimum time. It need not be the degree, the person who is most popular. It could need not be the person who is the gatekeeper or who acts as a bridge between all the information flow. This could be a separate person itself. We looked at that example of that scam in a corporation where the top leaders were not involved, but a person who is connecting two different teams together, marketing and sales or development or marketing team, they were responsible for doing this scam because they had access to this sort of information and they had reachability to all the nodes. Then we also looked at how can you create, there was this pairwise relationship. If two names are appearing together in multiple pages, how strong is their connection? We can calculate them by using number of times they are appearing together divided by total number of times they are appearing on the internet. Right, on the left hand side. Suppose there is a student and a professor. I want to check what is the co-occurrence. If two names appear in the same page, it implies a social tie. Tie is nothing but a connection or relationship. Right, tie is an edge. Okay, so we looked at Jacquard coefficient, which is, you remember, the number of times any person is appearing divided by total number of times they appear on the internet. But it has a problem. What if the professor is very popular? He appears at 10,000 pages, but being a student, he appears only at 10 pages. So if you do 10 divided by 10,000 plus 10 minus the intersection, it will be a very small number. So the overall value becomes very small, but that is not the true picture. They appear together in 10 places because the student only has 10 publications or has little experience as compared to professor. So what we did, we introduce this number of times they appear together divided by the smaller number, so that we are calculating this number proportional to the subject. Right, so it will be this red region divided by the number of pages student has appeared, because the other person is already very popular. So I just want, with respect to his own self, how important or how many times the person is appearing, the fraction of that number. So this fixes the famous professor penalty, this kind of division, right? So red region divided by the blue region, that's it. And it is more of a red region divided by a union of these two minus the intersection. So it can be wrong. It is just, the denominator is just about this particular person. So it will be a proportionate number. Then we understood that for humans to make sense of things, it is fairly simpler because we come from a similar background. We all talk the same language and we live in a same world. So if I talk about helicopter, if I talk about a building, if I talk about auto, all of us know what they mean, right? Because we have read somewhere. So we have that context in our brain, but not machines. So for doing the same thing, we needed ontology, which is a shared formal conceptualization of a domain. It is not a written definition anywhere, just a concept that if you want to if you want to share any information between a group, you should have a domain level conceptualization. Okay, so if I want to talk about humans, so I will say it's a physical being. It will have two hands, two legs, eyes, nose. It can walk. So all of this is a domain conceptualization in a common language which everybody accepts. Okay, if you talk about human, this factor features you have to use to explain, right? And all of us are different instances of a human class. Right, so class level or domain level definition is fixed. All of us, if we look at from the human angle, we are very much the same. But individually, our personalities, our hobbies, our interests could be different because we are just interests. We are instances of the human class, right? So we looked at two kind of assumptions. There is a closed world assumption, which is mainly followed in, say, computer science, or when you are doing a specific data analysis, where if some information is not in the data, you make a query, the answer could be no, no results found. That's it. But this is fine for a contained data set or a constrained problem or a use case. But while doing a social network analysis, we always assume the open world assumption. If it is not in the database, it is currently unknown. So it's just that I searched, but I could not find it in the current data set. So I cannot say for sure there is a relationship or not, right? In a data set, if you find a book in library, you enter the book name, you cannot find, then it is true that book is not available. But when you're doing the social analysis, what all books people read, so saying that this guy has never read Harry Potter books or does not like Harry Potter as a character, and you query the graph, you get no as an output. So your understanding will be that he might not have read the book so far. He might not know Harry Potter as a character. That's why he has no connection or no notes, no mention of Harry Potter on his blog. But this could change in future. So basically, we'll assume that we do not have all the data. There are always possibilities. So that's why you see this graph over here, and it has some dashed links. So unknown, there are always possible links to the unknown data. Then we looked at how do you define an ontology, what are the different frameworks. So we looked at RDF, which is called Resource Description Framework, and you represent the whole data as triples: subject, predicate, object. So Ram is person, Ram plays football, Ram eats non-veg, or whatever. So this is how you break down all of your data into a pair of triplets, right? And then you make connections based on that. So you basically define a subject could be Rembrandt. This is the one we studied. Rembrandt, I think this was a person and he knows other person. So we define tags. Subject is Rembrandt. Predicate is a friend of a friend, FOAF. He knows. So all of these are internally designed or defined for the computer to make sense of these two entities. And object is Saskia. Saskia is also a person. So this is how you will define that a person is a class, like human is a class. It has two instances. Rembrandt, he's a person. Person means where does he belongs to? So he belongs to the class person. Saskia is also a person, and person can know a person. This kind of relationship you define on a domain level. Then a person could be a thing, then it could be another thing. You can, like this, when create structures, drives a car or rides a bike, owns a hospital, works in a company. All of these tags you define so that you can define the structure. So next time, this is like the basic skeleton. Any information on top of it will be Ravi talks to this person, lives here. Some blog he wrote. This could be entirely understood in this structure. That Ravi is a person, he knows there is a relationship. This person could be an object. He works in a factory. He works for this corporation. All of this could be the tagging. So the underlying structure of any information. So chaining triples creates a directed graph. So you first of all define triples, and you connect them together, chain them together based on this information that you found online. You will create a directed graph. A knows B, B works at C, C has a friend D. You have an arrowed graph. And this is the resource description framework, basically the skeleton of how information should be defined. And then on top of it, we add a mathematical description logics, which are called OWL or web ontology language, basically, which adds the meaning to these relationships. Okay. Basically, you define disjoint classes, like what are the types of properties. A knows B is a reciprocal thing. If A knows B, by definition, B will know A. You cannot have Or can you have this kind of a relationship? Oh yeah, I know Shah Rukh Khan does not know me. So this is a directed thing. So I can define the property. Is it a symmetric property, asymmetric property, or a disjoint class? There are more than this. So basically all your properties will have some features. Okay, then why we need this sort of description? To figure out that there are multiple online platforms, there are different websites where users like us create their profile. So there could be there will always be a case a person is available at different websites, but there is no common identifying information. So if I extract that data through the internet, it will be treated as 5 different people, but ultimately he is just, or he or she is just one person. So defining this sort of ontologies, RDF and OWL, helps the computer to smush or merge the data which is coming from a similar source together and create a broader data set. So it is like on the left there is a person J Doe, he is from New York, and on another platform the handle Instagram is @JD. So and age is 25. So no information is common here, but the mailbox use the same jdoe@email.com. So this identifier, which is called inverse functional property, a value that uniquely identifies a single object, is used to merge them together. So now if you merge them together, you can create a mental model inside a computer that, okay, there's a person called J Doe, he lives in New York, his handle is JD, and he's of age 25, but these two are same person, right? So you use this rule called as owl.same as. So wherever you find the same mailbox, you merge them together and connect these two data set by using this same as. Now this will tell, this branch or this edge between two nodes will tell computer that, okay, these two are same person, so I should combine them together. If someone asks about, if I query about JD, it will give information about this node and this node both. That's why, because I could, they're connected through the same as relationship or the tag that I have defined based on the mailbox. If mailbox was not there, if they're using different emails, this will not work. So this only figure out the common uniquely identifiable properties like email, or it could be your phone number, it could be your address if you're using that online. Right. Then we looked at community identification in unit 3, where we are talking about the relationships or the edges more than the nodes. So first of all, we identify the highest edge betweenness, or if you want to figure out a shortest path, this edge lies in all or most of the shortest paths. You break that, then you repeat it again. So I think this was called the Girvan-Newman algorithm, which is a divisive method. You keep breaking it until you find the internal structure or how the connection works, right? So it has, any community will have dense internal edges and sparse external edges. So any social community will be closely knit together between the community and have smaller edges or weak connections to the outside world, right? So if you talk about, say, this class, so you are closely connected to each other rather than you are connected to the computational data science or, say, any other law department, right? There could be individual nodes who might be really good friends with them, but you as a community are very close together. I'm not talking about the mentally, but if that kind of activities, you all sit in the class together for a week, you are doing the same courses, you are being taught by the same professors, you have to submit the same assignments, you are writing this, you are making a similar kind of posts as per your assignment or something. So if we take all of this data and take similar data from law, there will be very less connections between communities, but all of you will be stronger. You have more connections. Right, centralities must be recalculated after every cut. So to figure out internal independent communities, we find the highest edge betweenness, break it, then get 2 graphs, and again find the highest, break it down to do a drill down or figure out the internal factions. We did in the last class, right? In the karate club, in Zachari's karate club, there was a tussle between the admin and the faculty, and the group divided into 2 parts, and we found out using this activity. Then we also looked at modularity or Q, a quality function to evaluate the network partitions. It is nothing but you have a community, you have a social network graph, and you also have a random graph. We called it the spaghetti bowl, which is basically I have 10 people. This is the actual data. How are they connected? And now I take 10 edges, randomly connect them, and see the number of edges in the actual graph minus the number of connections in a random graph. If it is a positive number, that means it's a valid social community. So a random graph is a spaghetti ball kind of a social network is, suppose I ask you to define a social community mathematically. So how will you start without any data? You will put some nodes and connect them randomly. I'll assume that this is my randomly distributed community graph. And to validate any other community as per this graph, this difference, the Q value should be positive. That's all. So basically, how my connections are there actually minus in a random graph, how are my connections? That's all. So don't look at these numbers, these formulas, but basically fraction of edges inside, expected edges in the random null model. So the null model compares the actual community density against a completely randomized version of the network. So in this particular class, you have some relationships, some connections, and if I take 5 nodes and just randomly connect them, of course, this connection, the real connection will be more than the random connections, because random connections do not have any pattern, but this real community is built on some sort of a pattern, right? So we just need to validate whether whatever model we are building is valid or not. Then we looked at the temporalness of the data. So initially, if you take a survey right now, whom you like, whom you don't like as an actor, or the kind of books you read, it will be just a snapshot in time of this particular day. But social network grows with time. Probably in the next semester, you take up a course, you get an interest in a different subject, you meet new people. Now you start reading different books which you were not reading before. You have a new favorite. So that's why we have to analyze any social structure or any social network with respect to time, so that we always we are able to track how the graph grew or how the graph split, right? So basically, there was this alpha factor we saw in the last class. So your connections today, alpha times your today's connection plus 1 minus alpha times yesterday's connection. So that we want to value both the temporal data and also present data. So it's like if I ask you, you have to choose between Salman Khan and Shah Rukh Khan. So you have some sort of a rating. Then 1 week after, I suppose a new movie comes in between. Next week also I take this data set, and then what value of what fraction should I assign to your today's answer, and what fraction should I assign to your earlier answer, so that I can value both. So it could be 0.5, 0.5, or it could be 80% today's answer, 20% last week's answer. So that in my ultimate evaluation, I can say that based on a temporal data or based on say a year of data collection and using this sort of formula, this is the user demand is. This is what a user is or a viewer is more interested in as an actor, right? And we also looked at decentralized OSNs or open social networks, which basically is the current internet that we are working on using right now. So earlier it was more of a organization owned. I am a company, I post information, you just read that. But now we can hold our own blogs, we can hold our own websites, we can invite people, we can form groups within platforms and talk. So it gives more power to peers. So it's called, say, P2P network, which replace corporate servers to ensure privacy and prevent censorship. Right? So now this is, I think, the last slide where we want to have a structure. So basically, all of you guys as social data scientists, you should have a structure which is given by mathematics, social network analysis, the graphs you make. Then you need some sort of semantic web and ontologies which will assign meaning to that particular graph, and you will need some sort of dynamics or communities and evolution. So you'll start from a node, we'll plot a graph, you will find some sort of central measures of centrality measures like degree centrality, betweenness centrality. We'll find some clusters, you will find some sort of edge betweenness, some sort of groups or internal communities, and then you will assign some sort of meanings based on the semantic data that you have collected. And the end goal is to come up to a conclusion that this is a community which has this sort of belief, or this is the group which like these kind of products based on your use case, right? And all of this we'll be doing it in Python. So next we'll be showing how to do the same in Python, whatever you have learned so far. So that is it. Now I am moving towards the Python script, which is this one. And let me, okay. So I do not have a data set, but we studied about Python in the last class, in the last semester, right? We all of us know Python. We did all the Python activities on the Jupyter notebook. This is Python is currently installed in my laptop, and how do you do that is by doing this. So you go to Google, search install Python, it will take you to a Python page. You install, download Python install manager, or you can pick up this one for your Windows laptop. If you have any other type of operating system, choose that one. Basically, it will install Python in your computer. Once it is installed, this black screen that you are seeing, it is called VS Code or Visual Studio Code. So if you have to write a document, you go to Word. You have to make a table, you go to Excel sheet. You have to write code, you go to VS Code. It is from a Microsoft. It's a code editor, IDE, Integrated Development Environment, right? And I have these files over here. So this is the just like the Google Colab notebook. I have this notebook and a requirements.txt file. So requirements.txt means I need to install multiple libraries, right? So the way to install is you can do just pip install, write a library name. Say I want to install NumPy, I want to install pandas, I want to install rdflib, and press enter. It will start installing all the libraries, right? Because you have just installed Python, but all these packages you need to install separately. Let me just stop it because I already have all of those. So you can install all of these packages. Now all the concepts, the RDF thing, the NetworkX, so basically the betweenness neutrality, plotting a graph comes from NetworkX. So I think you already worked on this. So it is already there in the system. So now I can start with the actual analysis, right? So our goal is to just practically look at all the concepts that we have seen in this unit, in this course so far. Right. So we are taking an example where we collected data from an online platform, and we kind of suspected that there are some bots. There is a user who is using multiple bots to promote his agenda. It could be buy my sneakers, visit my website, like my picture, or whatever. But it is not an actual person. We have to figure that out. Right. So we will be looking at ontologies, RDF, friend of a friend, semantic reasoning. We will create adjacency matrices, centrality measures, and we'll also look at community detection, right? So first of all, I'm assuming we all of us know, that's why I'll go through it in a quicker way, right? So basically we are just importing whatever we need. Graph, we need to plate, namespace is the URI that we studied. URI reference is again a link to the URI reference, right? Then we have OWL, which will impart the meaning to my graph. Okay. Then we now need NetworkX to do the betweenness centrality, creating the nodes and edges, right? And matplotlib we have seen in the last semester, where to plot something, NumPy to again to plot, Seaborn again to plot something, and NumPy to work with the numbers or do some sort of analysis, right? So let's look at let me run this one first. So just like on Jupyter, Google Colab, we have this sort of play button, right? We have it internally. It will choose, it should run directly. And let me hide this one. So yeah, toolkit is loaded. So it is basically printing this line. That means all of this code ran perfectly. So I have all the libraries imported in this current notebook, which I will be using for analysis. Right. So we intercepted the data scraped from various platforms. It is written in FOAF. So whatever data we scraped, it is in form of a friend ontology, right? RDF format. And we will have some nodes and edges. We need to plot. It is currently whatever my data I've extracted is in this form, right? So I am storing this. Since we have not extracted the data actually, I'm creating this over here. By default, you will have something like this, a huge amount of data, not just this small. So it'll be like if you're doing about a company, it'll be like say thousands of people and thousands of more than thousands of relationships between different people, and that's how you are seeing this. Okay, so I create a new graph. I will parse this whole thing into my graph, and I will print that data has been loaded. Right now, I want to visualize my graph, how my graph looks like. Okay, so first of all, I add the namespace. I'll use the same graph as above. I'll add all the subject, predicate, object from this description to create the graph, right? A knows B, B studies with C, drives D. So I need to, all of this information has been parsed as a network X graph, and I'm now assigning everything. SPO means subject, predicate, object from G dot triples. So in this graph, my graph name is G. In my graph called G, I have all of this information. These are nothing but just triples, in form of triples. So I'm parsing all of this information from these triples into a new node and a V called the edge. Okay, node U, node V, basically two nodes, and how are they connected? All of this information is being parsed to this graph, and I can plot this graph like this. Right, this is what my graph looks like right now. So there are like real users. This is just for this example. In a real case or an actual case, you will not have these naming. You will have something else. Username 123 at the rate this person or whatever person ABCD, right? But for this example, there are like 6 distinct users as of now, but it's not true. So basically, all of this information in form of triples. Bot1 is a person, and his name is Patriot1. Bitcoin wallet is this one. He knows bot2, bot3, and real user A. So bot1 knows these three people, right? And when I plot, it should say bot1 knows these three people: bot2, bot3, and real user A. These are the three connections I have right now. Right now, let's create a adjacency matrix on the same. So to create an adjacency matrix, again, 1 means there is a connection, 0 means there is no connection, right? I have the figure already. If you remember from Matplotlib, we can provide a figure size like this, right? And I will creating NX to a NumPy array. Basically, I'm converting the connections into a NumPy array, and I'm creating a heat map, seaborne heat map. Remember last semester flight data, in which month, how many people are traveling. Same thing we are doing, adding a title, and that's it. These are all the print statements for us to understand. Now, if I create, this is what my relationship adjacency matrix looks like. Bot1 does not have a connection with bot1. So that's why it is 0. Bot1 has a connection with bot2, bot3, and real user 1. So like this, we can see there is a dense collection of reds over here. There is a collection over here. An actual graph will be huge. 1,000 rows, 1,000 columns. And you will be seeing some sort of heat map or some sort of color coding there. So you can figure out, okay, which portion looks fishy to you, or you can evaluate any one of those. So now, look at the top left 3x3 block, bot1, bot3, they form a perfect dense echo chamber. It's a perfectly dense. So bot2 knows bot1 and knows bot3. Bot3 knows bot2 and bot1 and 2. So this group knows everybody. All of these three knows the rest of the three, and only talk to this particular real user 1 through the bot1 connection. Right, and real user 1 knows real user B and C. Real user B knows C, and B also knows real user A, and real user A knows C and B. That's it, right? These are all zeros. So the real user C does not know bot2 because this one thing is 0. Everybody can read the adjacency matrix, right? It is just a connection from node to node. Now the bottom right 3x3 block, they form a second echo chamber. We call them echo chambers as in a lot of chatter is going on this group. Like if you are in a huge class, you can actually identify a lot of noise coming from this portion. Noise is coming from this portion. That means people are talking too much there. It is just like that. So when you plot in an adjacency matrix, you can actually figure out what sections of the plot have some sort of activity going. Okay. So now you want to say identify and resolve. You can smush. You would like to smush things together because if you look at this data set, So this guy has Bitcoin wallet ID and they do not have. But you can see all these three bots have the exact same Bitcoin wallet. This is the same Bitcoin wallet they're using. Basically, same email they're using, same phone number they're using. So we can use this information to smush them together into one thing. So since it's a handcrafted example, in real world, you have to figure out or run this sort of semantic understanding that any node, if they're using the same IFP, inverse functional property, username, phone number, address, then they are essentially the same person. So let me run the smushing part of the code. So basically, this is the query we have written, which says that wherever the Bitcoin wallet is same for all the nodes, you collect all of that information, right? And you rename it to mastermind node or whatever, some false node or whatever you want to call it, right? So if you want to run this one, you get the machine directory that bot 1, bot 2, bot 3 are actually just one mastermind node. So he's that person who is running different bots to promote his page. This is happening actually in today's world. If you go to any YouTube channel, just scroll through the comments, you will find some random comments. So Bitcoin is raising in value, please invest, or look at my profile. No connection with the actual YouTube video, but just to make his presence felt online. There's a bot who will crawl YouTube videos and make your comment. You can do that in Instagram, Twitter, wherever. It's possible right now. Okay, so now let's make a mathematical graph after this sort of smushing has happened, right? So now what it has done is it has combined all the three nodes into one called mastermind node by using this particular code. So dictionary to store newly merged identities and so basically this query is searching for figure out all the nodes in the graph where the Bitcoin wallet values are same, and you add them in this particular dictionary and you give them this particular name. That's all. Okay. So now smushing has happened. Okay. Yes. So we are now rebuilding the graph based on FOF knows, and I'm adding both the all the nodes here and creating the graph, adding an edge between them, right? And I'm plotting the graph using matplotlib. This is the size and sorted in a sorted order, right? Number of connections. I'm converting the connections into numbers and heat map again, right? So what I found that mastermind node only knows this is the new node that has been created after smushing bot 1, bot 2, bot 3. And we're calling it as one big single node called mastermind node. And it only knows user A. It has no other connection, right? And all these other nodes, real user A knows mastermind, A knows B, A knows C, B knows A, B knows C, C knows B, A and B, right? This is how we smush data together and have a real efficiency matrix. These were the real users. That's why we could not find any matching property that can merge them together. So till now we assume they are separate users. Later in time, we might find that these two are also together or the same person. But we have to again perform this sort of analysis. Then let's look at the calculation of degree centrality, betweenness centrality and all of that. So it is very simple. This is NetworkX. It already has this property called degree centrality. So basically nx dot degree centrality pass your graph. That's it. And you can get real user A, the degree centrality is 1. Real user B, degree centrality is 0.67. Why? Because do we have a plot? Since user A knows all the other users, that's why it is completely connected. And other users B only know half of them, or basically 2/3 of them, because this node is itself no. So out of 3, it knows 2. That's why it is 2 by 3, 0.67. We did this calculation in the last class, but now in using Python, you can do all of this calculation just by using NetworkX. So basically, this is my graph, right? And I am just calculating all the degrees by using this inbuilt formula in NetworkX, right? Closure centrality, betweenness centrality, and eigenvector centrality. For node adding the centrality of its predecessor, right? The centrality of the node is the I minus ith element of a left eigenvector associated with the eigenvalue. This we have not seen in class, but it is also there. We have not studied in this particular course. But if you want to study, say, betweenness centrality of a node is the sum of the fraction of all pairs shortest path that passes through V. We know betweenness centrality is if you take all the shortest path, there are like 10 shortest path in this particular social network, and out of 10, 8 pass through Daniel because he is the CR. So he is has the highest betweenness centrality, right? But all of this calculation, we can do it in just one line of code. So basically, you just write this line, you get the value. No need to perform all this calculation with your hand. Okay. So degree centrality for each node, I have degree closest centrality for each node. Okay. Because you do it for each node. You can perform this calculation for each node, right? There are 4 nodes in my graph. What is the degree centrality for this node? B, C, D. Same thing you have for all the nodes. Real user ABC and the mastermind node. All of this. Betweenness centrality, all of this is here and this is here. Right. So what is my insight? Real user A and the mastermind have the highest betweenness centrality. They are the gatekeepers controlling the flow of fake news. Because in the above graph, we have already seen all the bots talk to only node real user A. So basically, what we can say that real user A is the person who is running this small racket of bots to promote his or her agenda, her business, or whatever. Like his or her Instagram page. And what else we can do? Yes. So now what you will perform. Now we are doing so let's visualize the graph again. How does my graph looks like? So this is my graph and the size by betweenness. So the circle, the size of the node is based on the betweenness. The bigger the circle, the higher the betweenness centrality. So all the 3, C, B and mastermind are same, but A has more because it has an extra connection, right? So now how will you figure out a community within this using Girman-Newman algorithm? Find the highest betweenness edge, cut that and do it again. So what you will do? So I am passing, so it is already a parameter within I think network X. You can get the communities within the graph. Just use this name, pass the graph, you will have all the communities. That hierarchical plot, first split, second split, third split, everything is there already. And you can add different colors just to map them together and again create the plot and cut the graph but show the connection in a different color. So now you can see that if you now delete this particular node, you have the community restored, as in the betweenness becomes the same. So now real user ABC all are equal as of now because we cut this connection. So this centrality has been lost. This betweenness or the edge connection has been lost. So all 3 are now kind of equal. So that's how we identify a specific community within a node, right? All of this is whatever we have already seen, right? And you can actually just hover over it, get all the definitions. If you want to understand what is happening behind the code, right? So we are creating a quarantine graph. This is what we have seen in the last class itself. So fake news is quarantined, election is safe right now. So this guy was some sort of using his bot network to create fake news about an politician or about some other competitive business. Could be anything. In this example, it is about, say, elections, and this guy is bad mouthing all the other parties using their bots. But we figured out performing this sort of analysis. So that's how we use the concepts of social computing and data mining through Python, which is very simple. So we spend around 2-3 months to understand all these concepts. But for Python, it is just one line of code. You want centrality, you want to plot a graph, you want to give a adjacency matrix, you want to find a community, do that divisive elimination of the no edges. You can do all of that with just few lines of code. That's it. But you need to have all this is possible because all of our data has this sort of underlying structure triples, A knows B, B drives C, studies with D. All of this information has been captured semantically. That's why we are able to perform these sort of analytics, right? So this is just an example, but you can perform this on any sort of data set. And probably I will suggest that we should have hands-on for this course from next semester onwards. Okay, so this is it. Let me just stop.